All right, thank you. So I'm Daniel Reynaud. I'm a PhD student in France, in a third-year PhD student. I work in Nancy University, and I'm going to explain you what dynamic binary instrumentation is for those of you who don't already know what it is. I'll be going to explain the concept, and we'll all build together some examples. And I'll try to give you some meaningful examples of what you can do with it, how it works, and how efficient that is. And especially with a focus on malware analysis, because that's what I do. And hopefully that will be interesting. The goal is that you understand the stuff that I'm trying to explain. So if you have any question, really feel free to interrupt, and that's it. So I'm going to explain exactly what DBI is, and I'll first give a quick overview of the different tools that exist. So you might know some of these tools. They are the most famous. They are getting more and more used today, because DBI is not a new concept. It's actually quite old, but it's getting used because now you have some really interesting tools, and they can do good stuff. So there is Pin, which is the one that I use most. It's a proprietary DBI engine. It's made by Intel, and it works on both Windows and Linux, 32, 64 bits. And we use that in experiments on malware analysis. I'll give you the results just after that. There is Finegrained, which is an open source project. There is Dynamic, which is now which has been bought by VMware, which is also open source software. It's kind of a competitor to Pin, so if you don't like Pin, you can use Dynamic and vice versa, I guess. And now you can see that some reverse engineering projects are using these tools. It's interesting because none of these tools has been made specifically for reverse engineering, as I guess we understand it. It's been used mainly for general purpose software engineering, doing such like profiling and finding memory leaks and this kind of stuff. Whereas us folks doing security are more focused on malware analysis, vulnerability research, and this kind of stuff. So they have not been made for that. And sometimes you can feel it. But I try to show that even though they've not been made for that, out of the box they work quite well for what we can do. Some of the known projects that use them are Microsoft tool, Sage, who they do fuzzing, what they call white box fuzzing, automatic white box fuzzing using their own DBI engine. There is an equivalent project, Finegrained, by Sogeti, who uses Finegrained as a DBI engine. So they do vulnerability research with that. They develop, well, it's clever fuzzing. Let's call it that way. There are people doing exploit development with that. For example, Sean Helen uses Pin. It's good stuff too. And some people also do unpacking. I'll give an example of unpacking, how it works. So you can use some of these tools to do interesting stuff. So I'll try to define now informally what DBI is. I really thought a long moment about that. It's not really simple to get a good understanding of what DBI is, but so I'll try to give my understanding and how to characterize what DBI is. So first of all, it's a program transformation. It works by rewriting the programs. That's a really fundamental feature. I'll give examples of that later on. And the second point is that this transformation, the purpose of this transformation is to give you full control over the program. So you take an unknown binary, you rewrite that, and once it's rewritten, you can execute it, and you have full control over what's going to be executed. This is really important. I'll also give examples about that. And additionally, I added that you don't need architectural support. This is interesting for me because, for instance, you don't have to know how. You don't need any privileges. I mean, the interpreter or the CPU doesn't need to know that you're doing DBI. You don't ask the permission to anybody. You just rewrite stuff and execute it. So you don't depend on any architecture. You don't depend on privileges. You don't depend on hardware features. You actually depend on nothing. And this is a good option for me. So let's compare that with some of the other reversing tools. And let's contrast it. For instance, if we take virtualization, you don't have full control on the program. It's a bit like debugging. It's an event-based analysis method, so you don't have full control. You ask the interpreter to give you control sometimes, and then you give control back to the interpreter. In between, you don't know what's going on. So this is quite different with regards to that. You have emulation, which is equivalent to interpretation, which means you take a program that you don't modify, so you have full control over it, but you don't rewrite it, you just interpret. It's just a simple fetch, decode, execute loop. So it's not program transformation, so it's not exactly DBI. As I said, debugging requires architectural support, so it's also different. I think we can compare it with virtualization in this regard. And finally, there is dynamic binary translation with stuff like QEMU, for instance. And it actually matches my definition. I mean, DBT has these three properties, so it can be seen as a special instance of DBI with a different purpose, which is just execution, not spying on programs. So if we try to contrast it, here is let's say a nice picture, an overview of the different components. What I put in red each time is the analysis components when you're reversing stuff. When you're doing debugging, you're sitting next to the program you're trying to analyze, and you're asking permissions to the interpreter to give you some information about the program you want to analyze. When you emulate, you actually replace the interpreter, so you sit on top of the interpreter, and then you can do what you want with the program. And then when you use a software interpreter, like for instance, when you want to analyze JavaScript, which we'll be doing later on, or when you do virtualization, you actually sit in the interpreter. So either you change the interpreter, you modify it to log some events, or the interpreter has, let's say, a sort of plug-in interface. This is the case with virtualization. And then there is DBI, which is really different from the other techniques because it works by changing the program, as you could see pictured with the weird color there. And the analysis component actually lives inside the program that you want to analyze. This is also important to understand. So I'll try to explain how it works, and then we'll build an example together. So it works by giving you full control, as I told you, but without emulation. This is not just a technical detail. This is a really fundamental difference. Because when you do DBI, you rely on something existing. You take for granted the fact that you have an existing interpreter. And it can be very complex. So you're really glad that it exists and you don't have to implement or mimic it. It's there, and you rely on that for the execution. And you don't have to modify it. That's really important. So you have this CPU, it's complex. You don't need to understand or modify it. It exists, and you rely on that to execute the stuff that you want to analyze. So you don't have to know the full semantics of the code that you want to spy. And this is really interesting, especially in the case of x86. Really, this is a huge benefit. The semantics is so complex that it's really painful to implement fully. And the guys who do malware exploit this fact, and they use anti-emulation tricks because you can never embark the full semantics. It's just too complex for that. So you're really glad that you don't have to know it all or to implement it all. And as I said already, you have no requirements for debugging. So you can have full control without that, and this is good because even in some hardware cases, you don't have hardware support for debugging, for instance, GPUs. So this is a bit of science fiction here, but you could imagine a DBI engine working for GPUs, and I mean, you could emulate the behavior of a debugger with DBI without the need for debugging support. So this is science fiction, but it should be possible, I guess. So now, how do you achieve this full control? This is a bit theoretical, but I think really that's whatever the language or architecture you're targeting, if you want to write a DBI engine, you have to implement these 4 steps. So the first part, the requirement is to parse the code. You just have to read this. So you want to program a DBI engine F. and you take a program, which is code, and you want to analyze code, okay? So you have to parse it first. This is, well, this is not a strong requirement. You have to know how to read it. Then optionally, you will modify some, what I call user-defined program points. So you have to spot the interesting program points, which is what you actually want to, what we want to spy in the program. Because if you're doing reversing, you are looking for some information. Well, you have to define these program points where the information lives, and modify these points to extract the information from the execution. So I put that optionally because that's, well, you can have a generic DBI engine without doing that. This depends on what the user wants. Then the really important and tricky part is how do you know that the code that you want to analyze won't escape your analysis component? Well, what you have to do, and it really depends on the language or architecture you're targeting, but you have to statically find the points where you know you will lose control, and at these points, you have to insert calls to yourself. And this way, when the code is reached, the code that you couldn't find statically is reached, you know that you will be called. So the goal is that no code can be executed without you seeing it first. This is really important. Really important. This is what makes it powerful and useful, but depending on the language, this can be quite tricky. Once you've done that, you've read the code, found the interesting program points, and rewritten them so that you can jump into new code and can check it before it's executed. You just can run it. So you have to be pretty confident that you've done things well, because you've rewritten a program potentially malicious. And you're confident that your rewriting will retain the control. And then you can just run that instrumented binary. So this can be seen as just-in-time compilation, because you're actually recompiling or modifying new code each time it's found, each time new code is generated or discovered in a user program, in the target program. So this is a form of just-in-time compilation, if you want to have a mental handle on that. Or another way I like to see it is very much like program infection. It's almost the same like when you write a file infector, you have to find the entry points and you have to hijack that so you have control before the target program. And then if you want to retain the control, you have to also find the interesting program points. And this is almost the same, except that, well, you're not self-reproducing, so you're not a virus, but the idea of hijacking the control of target program, well, it's a bit like, you know, an alien-like infection, like, you know, the face huggers and stuff. Well, once you have hugged your victim, you just can't let it escape, so you can also see it like that. So now the advantages and disadvantages. So first, it's a program transformation. I'll explain that a bit later. And the performance is also quite good. The problem is that the cons are exactly the same. So let me explain that a bit. The fact about the program transformation, for instance, I put it in the pro because if you rewrite the program, you actually control it. So this is a benefit. You really can control, and you can drive the execution where you want, and you can lie on the inputs, and you can change the outputs. You can really control totally what's going on. But it's also a problem because if the program that you're targeting is doing integrity checking or this kind of stuff, if it uses code introspection, tries to self-checksum itself or this kind of stuff, you've changed it. So it can be a problem. It can refuse to run, or it can change its behavior. So the information you extract becomes wrong. So that can be a problem. It really depends on what you want to do. And then the performance. I put it in the pro because well, I have a bold claim. This is fine-grained analysis, and I think that DBI is the fastest method for fine-grained analysis. Or if you want to do instruction-level analysis, I mean, DBI is really the way to go. It's the fastest. It's a lot faster than single stepping, like debugging, or it's a lot faster than emulation. So really, I think this is the fastest method. But this is my opinion. You can prove me wrong maybe on that. But I also put that in the disadvantages because, well, it's fine-grained analysis, so it's costly. So if you want to just look at some program points, and you might not need fine-grained analysis, so sometimes it can be overkill for what you want. And you say, oh my God, it's it's totally slow for what I want to do, but you just should be using fine-grained analysis in the first place. So really, whether it's an advantage or a disadvantage really depends on what you're trying to do. So now, what we'll be doing that we'll be building together a JavaScript deobfuscation engine. So it will be based on DBI. We'll illustrate the ideas I've just explained, and we'll see how it works and maybe try to get some results with that. So I just showed you the pseudocode for what you needed to do, and well, this is the actual JavaScript code for what you want to do. This is a generic JavaScript DBI engine, and well, since it's JavaScript, it's almost like pseudocode, so this is quite readable. So you want to define an instrument function, which takes a script, of course, as an argument. So in this case, script is a string for us, but this string will be executed once we've rewritten it. So the first step is to replace the eval function with yourself, so the function instrument. We need to do that because we assume that eval is the only way to execute dynamic code in JavaScript. So the eval function takes a string and interprets it as a JavaScript code. So if we find an eval in a script, we know that we might not know statically what is going to be evaluated. So we have to control that, and the way we control that is by replacing the eval function with ourselves. So we have a way to analyze the code and instrument the code, dynamic code that was going to be executed. Then in the comments, well, if you add other replace function calls, well, you will do other interesting stuff. For the moment, well, we just do nothing. This is a generic engine, and then you can add whatever instrumentation you see fits. And in the end, because we actually need to execute something, we eval the instrumented script, because once it's rewritten, that's it, we can run it. So as you can see, it works in a way statically. The rewriting works statically, but it also works by inserting calls to yourself dynamically. So it's really a mix of static and dynamic analysis, okay? So now, what if you want to add deobfuscation behavior? So we'll take a simple example. What I've often seen in malicious scripts in hacked websites, for instance, is that they often use document.write function call so that they can add other scripts or other images or invisible iframes or this kind of stuff in the web pages that they have hacked. So what we might want to see is, first we want to prevent these document.writes from happening, and we want to see them. So if we take an obfuscated script, and this script is actually writing stuff, malicious stuff in my web page, I want to see it. I want to log the writes instead of executing them. So the way we do that is by adding another replace. So we find the document.writes, and we replace them with a log function. So the document.writes are no longer executed, and instead I see them as the analyst. And again, I'd like to stress the fact that, okay, statically this is nonsense, because you're going to say, okay, if it's in an eval, you won't see it. And the point is, well, we have replaced eval. Eval is now us, so no code can be executed that has no document.writes replaced. So this is the point. I'll be doing a quick demo now. So the prototype is called crème brûlée. You probably don't see anything. This should be better, I guess. Okay, so the way it works is that, well, you have two boxes, an input box, you put your script that you want to instrument, and then you have the output box. I mean, couldn't be simpler than that. So let's try to see what happens when we do a document.write. And I guess you can guess the result. Okay, when we click go, we instrument that and we run it, as you guessed. And the output is that we can see, well, first, the page has not been modified, so the document.write has not occurred, but we can see the log. And in the log, we can see that we have intercepted a call to document.write with the argument bad stuff, which is what we wanted. So, okay, the replace work, we're all happy with that. well, you're probably not convinced right now because you say, okay, well, this is silly. I could see it clearly that it was going to write bad stuff, so what's the point? So first, I want to prove you in a way that the code is really executed. For instance, by executing something that we're not interested in the instrumentation. So if I do an alert with something, the instrumenter won't do anything because it's not an interesting program point. So if we run it, well, it actually runs. You can see the alerts going on. So this is just to stress the fact that the code is really executed. It's not just statically analyzed or this kind of stuff. It's really, really executed. Okay. So now I'm going to convince you why we need to execute it because, well, we really, really need it. So let's make a more involved example. So what I'll do is a document that write again with a variable. And this variable is actually computed and not just an immediate value like I just did before. So let's compute it. Okay, you get the idea. I'm doing random stuff here just to show that the computation of the variable s here can be arbitrarily complex. You can do it really. You can make it as complex as you want. Okay, it can be crypto, for instance. So statically, you can potentially say absolutely nothing about s. So you have to execute it to see what's going on. So now, if we instrument that. Well, we see in the log that we intercepted the document.write, and we see in clear the argument, of course, of the document.write. So this is the whole point. You have to execute that stuff to see it. So you can also see it as a form of lazy evaluation, like saying statically, okay, I see a document.write, but I have no idea what it's going to write. So let's replace it with a log function and execute that, and when it was going to be executed, we'll see what was the actual argument anyway. So this is a way to bypass obfuscation. Well, I hope everyone's following me right now because we're jumping into more advanced stuff. So for instance, now we are going to do dive into dynamic code. What's happening if we do this dynamically? For instance, I take the same example, same script. I just put the document.write in an eval call. So the document.write becomes a string, and this string I ask it to be executed dynamically. So let's see what happens. Okay, we can see an additional line that wasn't here before. So again, we see the log document.write and the argument of document.write, so this is fine. And just before, the instrumenter warns you that there has been dynamic code. So statically, he sees a call to an eval function. And he says, okay, this is going to be dynamic. I don't know what's going to be executed, so it inserts itself right there. And when it's executed, again, it logs the results. And as you guessed, you can embed as many evals as you want. You can put 5 layers or X layers of dynamic code, and each time the instrumenter will jump right into it. And in the end, when stuff is executed, you'll see it. This is the point. So again, if you try to make this just a bit more complex again, because, well, this is not really interesting. You're saying, okay, eval, we're giving it a static immediate values. It's not really interesting. But again, if I want, I can make it as complex as I want. So for instance, I will actually compute the value before giving it to eval. Okay. So I have 2 additional variables, and now what I'm going to do is this. Okay, so this is just an example to see that eval can take, of course, variables, not just strings. I mean, it's a string, but it's computed. And again, the way it's computed can be made as complex as you want. So if the code that is going to be computed is encrypted or compressed or this kind of stuff, again, statically, potentially you can say nothing about it. But here, if we execute that, well, again, you can see the dynamic code, and now you can see it in clear because you can see the computed value of the dynamic code, the argument of eval, and then the instrumenter jumps right in, And you can see the document.write happening and clear with the argument. So that's the point. And of course, you can make this as obfuscated and as complex as you want. You will still see the result in the end. Let's take an additional example, just to illustrate the full control. I told you earlier that you have full control over what's going to be executed. So let's check that. What I mean by full control is that, for instance, you can lie on its inputs. For instance, if it's trained to take some inputs from its environment, well, you can intercept that, and you can lie and put the value that you want instead of the real value, and this can be interesting sometimes. So for instance, if you have a script that tries to read navigator.userAgent, well, it's executed because we don't instrument alerts, and you can see the actual value of my user agent. And sometimes this is bad because some malicious scripts try to do that just to check that they are in a real browser and not in an analysis environment. So sometimes the actual behavior depends on the browser, the user agent string. So you might want to lie to it and change these values so that it exhibits different behavior. So I added an option here to change the value of navigator.userAgent. And we can put what we want here. And if we execute again, well, I can see that the value that's read by the program is actually my own value. So again, the point is that I did not actually change the navigator.userAgent string. It's still there in the environment, and it still has the original value. But the thing is that I control the script. So I can lie at the moment when it reads. I can put another fake value inside it, and the script has no way to know if he's reading the actual value, the real value, or if he's reading something fake that I gave it. So you can play with the idea as much as you want, but it's really powerful because you can really fake inputs, you can control stuff, you can drive the execution where you want, so you can force the actual malicious script to exhibit different behaviors. Okay, thanks. Well, so that's it for the building of the example. So now, if you want to add more deobfuscation features, well, you have lots of other interesting program points to instrument. I'm not going to detail everything because this is not a talk about JavaScript obfuscation, but you would have to monitor changes to location.href, for instance, for if a script wants to redirect you to some page. Of course, calls to new image because sometimes they want to download advertisements, all this kind of stuff. Calls to, for instance, new ActiveX objects. Some scripts do that to trigger exploits, all this kind of stuff. So anyway, you can have an arbitrary number of program points that you want to instrument. And the interesting point here is that well, it's just adding a replace. If you have a new trick that you want to analyze, just add a replace and you will see it. So this is really scalable. I mean, if you want to monitor malicious scripts. So I have another demo. So what I've done is that I've found a few malicious scripts on hacked websites, and we'll try to see how the DBI engine works on these malicious scripts. So this is an actual malicious script. I mean, really found on a hacked website. I mean, it's obfuscated, and obviously I don't even want to bother reading that. I trust well, the instrumenter to give the good result, and you can see that, in fact, the script does a document.write, and you can see it's trying to insert an iframe, and well, I can see it in clear. Let's take another example. This was on a hacked WordPress blog. Again, I put it in my input scripts. Let's clear the outputs. So again, it's a bit more involved, and again, I don't even want to read that. And then you can see again in the clear, it's doing two document.writes, and it's adding a script, and it's adding an image, and that's it. You don't even want to read the stuff. You just need to look the outputs. And then an example a bit more involved. This one's getting big. And again, I really don't want to read that, but you can just see what it's doing. And this one is interesting because it adds a script, again a document.write, and it adds a script. So what we can do is again take this new obfuscated script here and unpack in a way this second layer. And this is it. Now you can see in clear that it's adding another invisible iframe. So that's 4 clicks away. And well, that's about it. Well, let's do the massive example at the end. So that's it. This one, you have a big output because you can see that there are several layers of dynamic code that are executed. Again, you don't care because the way you instrument is that recursively you jump into dynamic code, so you can jump successively in the different layers of dynamic code. And in the end, you see that you have a document of create element and stuff, so you see it in clear. This is just to illustrate the fact that you don't care about the number of evals that are called. Each time you just jump right in. So that's it. You get to the point where the malicious payload is being executed. Well, that's it. Of course, this is not a full-blown deobfuscator. You'd have to do other stuff. I won't detail that. And especially you'd have, of course, to manage code introspection, as I told you. You'd have, because sometimes the scripts try to check if they have been modified and this kind of stuff. So this is not fully operational, but well, it works okay on real life malicious scripts. So that's not too bad. So now a quick demo on x86 unpacking. So now for this demo, I'm using Pin, so we're no longer playing with a JavaScript DB engine. I'm using Pin, which does x86 instrumentation on Windows and Linux. So this is my backend for instrumentation. I use it to record execution traces, and especially execution traces of packed programs. So the question is, what happens when you extract a run trace? So with Pin, my DBI engine, and you import that trace in a disassembler. And I'll show you the results right there, because just a quick reminder for those of you who are not familiar with Packers. Packer is a program that takes another program, transforms it into data, encrypted, compressed, whatever, and then you can only see the green envelope. You don't see the packed program, and this is, of course, the gray program that's interesting. So if you put that in a disassembler, such as IDA, well, you just see the envelope, and that's not interesting. This is not what you want. So what I propose is this. You run the packed program with a DBI engine, you extract a trace, which should actually be both green and gray, but anyway. And then if you have a way to import that trace in a disassembler, well, we'll see what you get right now. So I made a quick video. So just to show you, you have a program, host name, packed with AC protect, or random packer, whatever. We have executed it. You can see that it's actually executed. You have the AC protect warning because it's trial version and stuff. And then what we want to do is we want to trace it. So we jump into my tools called Tartatan tools, and then we run it with some command line arguments. And the goal of doing that, so in the backend, it's called Pin on the program. So you actually execute it, and at the same time you execute it, you dump a trace, a full execution trace of every instruction that's going to be executed. And you can see that a trace file has popped up, and it's being filled by Pin. So I'm jumping right now because it takes some time. It takes about 30 seconds to execute. That's it. You can see that it actually executed. You have the warning about the trail stuff. And then if we execute head on the trace, you can see that it's an actual trace file, so that's why it's a bit slow. And you can see that, well, you have lots of hex stuff. But basically, it's a hex dump of every instruction that was executed. And then if we import that in IDA now. So now we're in IDA. We open the packed program. So as I told you, we only see the green envelope, which is basically nothing because there are a few push threads, and IDEA doesn't follow that by default. So we see only 3 functions and basically almost no code. And then we run a Python script, and this Python script takes a trace, and its job is to import the trace inside IDEA. So again, it takes some time. So in real life, this would be the moment to go grab a coffee. So since it's a video, I'm jumping at the interesting parts. So check up there in the memory representation area of IDEA. You can see that stuff has happened right there. I'm going to play that again because I love it. So you can see in the gray bar up there, basically no code, nothing. Gray means unknown to IDEA. And now you can see that code is popping in, and this is all the actual code that was executed that has popped in. So now IDEA has found all the functions that have been executed, and now we have the actual code that was executed by the packer. If it's green, it was executed, and if it's white, it was not executed. So this is just a random browsing inside the trace. So in this case, we use IDEA to visualize the trace. And of course, what's interesting in the trace is that you have all the information that was contained in the program, including, of course, the packed program. So in orange, we can see dynamic code that was executed by the packer. And in the comments, you can see the number of the layer, or what we call a wave. And IC Protect is interesting because it has lots of waves. So what you want to do is unpacking, you can just ignore waves 1, 2, 3, 4, 5, and just jump at the end, because this is where the code was unpacked, and you have the actual code that you want to see. Well, that's it for the demo. I think you guess what it does. It's really simple. I just wanted to illustrate that it's really simple and effective. So this is really lazy unpacking. Unpacking for lazy guys. Let's say it's just execute trace, import the trace, and you have everything in clear. So just a quick note, PIN, as I told you, has not been made for that. It's not been made for malware analysis. And I wanted to answer the question, okay, how well does it work on malware? And the answer is not too bad, actually. We tried it on 16 packers. It works out of the box on 14 of these 16 packers, so this is not too bad. And then we've run it on a few malware samples that we've taken from a honeypot, actually 100,000 samples. Taken from different honeypots, and well, overall it works in 80% of the cases. We have a pretty consistent number there. So, well, for something that has not been made for malware analysis, it works quite well, and it's pretty effective. So if you're interested in the results, you can go check out my blog. I posted some of the results there. So that's it. I'm jumping to the conclusion. So I hope I've convinced you that instrumentation, DBI, is a high-level, elegant technique. You see, the idea is simple. The concept is pretty simple, but it's something elegant, and you can ensure that you do good stuff if you're interested in that. But what's cool is that it's high-level, so it means that it saves time. You don't have to write hundreds and hundreds of lines of code. But it solves low-level problems, which are usually quite involved. So this is really interesting. As I told you, this is a mix of static and dynamic analysis, which is good because you have the advantages of both. And it also works on any language. This is why I tried to show side-by-side x86 and JavaScript, which are two totally different stuff, but by using the same ideas, well, you can perform interesting stuff on that. An additional point, which is pretty important for me, that it's algorithmically sound. Unlike debugging, for instance, or virtualization approaches, you see everything that's going on, and you control everything. This is a really interesting point. And my trader's claim, as I told you, in my opinion, this is the fastest method if you want to do instruction-level analysis or really fine-grained analysis. So consider it for your own projects. And my real conclusion base, is that I have GPL the tool. I've released them yesterday, actually, just for the conference. So if they are available, they are free. You can, well, play with them and use them. Be aware that they are really experimental. But they work on actual malware samples. So that's it. Thanks for your attention.
Right. So we have the lunch break now, but We start a little later, so we'd like to take some more of your questions. So if you have a question to Daniel, please let me know so I can give you the microphone.
Have you tried debugging or instrumenting heavily threading code? Because usually in these obfuscation examples, one of the threads is responsible for looking at the text segment that the modifications are still in place, and you are modifying code, so I could think it should be hard to circumvent this, or is this the 20% you can't debug?
Well, so the question was about multi-threading. Well, for the moment, we don't handle multi-threading. This is a quick answer. And this is a concern, of course. So yeah, we should do that. If we want a full-blown production-ready stuff, of course we have to manage multi-threading. I just tried to implement the simple multi-threading model and found out that it worked quite well. So I did not manage all the complexity of the multi-threading, but yeah, of course this is something that you would have to manage if you want a production-ready product about that. Well, about the 20% that don't work, it might be it might be that it uses multi-threading or this kind of really sophisticated integrity checking. But in my experience, I tried to run some of them manually, and most of the time it's just that the binaries are actually broken, or they just don't execute at all. So it's not, I don't know how prevalent multi-threading and such advanced integrity checking, really, I don't know how many malware samples are there. Yeah.
Skype, is an example of heavily multi-threading code.
Yeah, okay. So Skype is an example of self-modifying code, and I actually tried to instrument Skype, so this is funny. And well, it works up to some point, to the point where the actual multi-threading and integrity checking takes place. So this is true. About malware, I don't know how prevalent this is in malware. So this is an actual question. I don't know that this number.
Any more questions?
Yeah.
This is actually a follow-up question to that. If you were to try to make it capable of investigating multi-threaded code, do you think it would be a real large hurdle to overcome, or do you think it would just be not so difficult, just a little bit more work? And do you have any estimate there?
Well, the question is, how difficult would that be to add multi-threading support? The good news is that PIN already manages actually multi-threading, and this is good because PIN is my backend for x86 analysis. So my backend does this, and I just need to model that in the traces that I export. So I expect it would not be too much work. It's just that in the trace for the moment, it's a really dump trace, just dump stuff and expect that it's in sequential order and this kind of stuff. For multi-threading, you could imagine dumping one trace for each thread, for instance. So I don't expect that to be a big overhead. You just have to model it. I mean, it should be quite simple, yeah, I guess.
Another question. Usually you have some thread in malware that looks over the text segment that nothing is modified. Would it be possible with your approach to have different instrumentation for fetching code for instructions and fetching code for reading the code? So we could subvert these checks by simply returning what the code would expect is in the text segment, yes, while there is something completely different.
Yes, so the question was about how could we lie to the integrity checking code, if I understand that correctly. And this is a question I tried to address, and I made some tests on PIN, for instance, and well, in some cases, as I told you, you have full control. So if the program is trying to read some inputs and the input happens to be itself, well, it's still an input, so you can still lie to. So, for instance, if it tries to read the modified code memory, You can see that. You can see that it's trying to access a modified part of memory, and you can lie to it and give it the original value that it expects. So virtually, yes, you can lie to it. And PIN, in some cases, manages that pretty transparently. Yes, this is a massive question for DBI engine tools. How do they manage introspection? And in some cases, they do it quite well. So we benefit from that when we do the front end. But yes, this is one of the really tricky questions of DBI, and interesting too.
Yes, any further questions maybe?
Quick question. Yeah. Why are you concerned about executing the malicious JavaScript in your instrumentation system?
Okay, so the question is about what is the risk of executing malicious JavaScript in my instrumentation code? Well, the risk is that if it's really malicious and it does stuff that my instrumentation didn't manage, it might escape, and in some cases it might try to exploit something. So you just have to be aware that it's malicious. So by definition, it is tricky. So if it uses some tricks that we didn't think of, it might escape and it might do bad stuff. So this is just a reminder that this is not totally safe. If it was purely static analysis, I mean, you can just input it, and that would be totally safe. You would face absolutely no risk. Well, if it's malicious, you don't always know what it's going to do. So as you could see, I was running the examples in the Chrome browser, and if I'm trying to run a malicious script that happen to exploit something in the Chrome browser, well, I'm going to be exploited. So you just have to know that. It might not be a serious risk, but just know that you're actually executing stuff. So this is just a risk that you have to know about.
So if there's no more questions, I'd like to wrap it up. Just before we go into the break, I give you some more information. But for now, thank you very much, Daniel.
Okay, thank you.
Thanks.